I want to discuss slight difference between the way engineers approach problems versus physics. And this is just my basic thoughts. This is not something written in stone. I've just noticed over time that physics problems phrased in school tend to be let's get the numbers for this particular situation. So you might calculate the speed of a bullet from a known quantity of gunpowder in the barrel or from a direct observation. An engineer, on the other hand, might have a situation where he requires something to travel at 1,000 meters a second, and he has to calculate the requirements necessary to do the given goal. They're the same problems, but they may be approached from backwards to each other and sometimes can cause some confusion. So let's look at a typical question in a physics classroom. We say a 2,000 kilogram load is lifted 150 meters in 10 seconds. Calculate the power needed to do this. Step 1, we calculate the gravitational potential energy, E equals mgh. We get about 3 million joules to lift this elevator up. It's lifted in 10 seconds. We get 290 kilowatts, would be the easiest way to phrase this, which is a lot. Since you have a 2 kilowatt hair dryer, 290 kilowatts is quite a bit of electrical power to do this job. But an engineer might be phrased a little bit differently.
Ms. Fearon, please call extension 258. Ms. Fearon.
Ah, yes, the dulcet tones of the secretaries, like songbirds in the morning. Instead, the engineer is faced with this. He gets told, no, you can't go faster than 20 meters a second. That's it. We want to go to 20 meters a second in the elevator. Beyond that, people start freaking out. The air pressure changes too much. So now we need you to work out what kind of motor do we need to do this 10 meters a second up or 20 meters a second up. The first part of the problem is no different. You calculate your energy, it won't change. But now what we need to know is the time. Given a 150 meter building and a maximum speed of 20 meters a second, this means we could be up the side of the building in 7.5 seconds. So they're going to want us to give the people a fast ride. If we were only going at 10 meters a second, it would take 15 seconds for the trip. But we want to go for the maximum. So the shortest duration will give you the maximum power, right? If time is quick, the total power will be higher. So we take our 290 kilojoules, divide it by a 7.5 second shortest possible trip time given this engineering limitation, and we get a 386 kilowatt motor. So the engineer is given parameters. You can't go faster than 20 meters per second, so calculate the power of your motor. And anything beyond that 386 kilowatts is gravy. It'll work at less than that, but the speed of the elevator will slow down.
Mariah Singh, please come to the office. Mariah Singh.
Now let's make a pretend scenario where an engineer has to balance two rules. Let's say you're told you can't go faster than 20 meters a second on an elevator, but then a new safety rule comes in that elevators must be able to get passengers to safety in under 1 minute. So you have 400 kilowatt motors you're going to install on a 2,000 kilogram elevator car, and they're going in the Burj Khalifa at 828 meters in height. Can you pull off the trip with this kind of motor at that speed in under 1 minute? What do you need to solve for to answer this engineering problem? Well, the easiest thing to do is calculate the energy to lift that elevator to the top of the building. And I've got the wrong number here. Okay, so that was 828. I put in 700 meters instead. So assuming that number there, okay, yeah, so I've still got the wrong calculation here. We get 13 megajoules in 60 seconds means a 228 kilowatt motor. You were given a 400 kilowatt motor. It looks like it's good. I think if I change this to 828, you're only going to get about 10% more, so you'll still be under 300. My bad. Now, how long is the ride going to take up the side of the building? For that, you go back to kinematics. Given that speed is distance over time, you can solve for time by dividing these two, and you get 41 seconds. Now that one I carried out with the correct numbers. So you're safe. Both things can be achieved. The question would be, if we gave this 1 minute evacuation rule, what would be the maximum height of any building if that rule was enforced? Now here would be another one. You're a safety engineer in a mine, and you're supposed to provide an ability to get the men out of the mine in case of a power failure. So they show you a 400 watt, like little Honda gasoline generator, and it's supposed to be able to power the elevator shaft during a breakdown. The elevator shaft is 150 meters deep, and again, I'm going to use this 2,000 kilogram load. Can you pull it off with this generator system they set up? Well, first thing again, that number hasn't changed. They kept it the same throughout the problems. We've got 3 million joules of energy we have to provide to get them out of there. If we work this out, the 3 million joules being provided for at 400 joules a second. Power is energy over time, so time is energy over power. That's like saying you want to earn $3 million and I'm paying you $400 a second. How long is this going to take? So 3 million joules at 400 joules per second gives us 7,250 seconds on that generator. That's like completely unacceptable. 2 hours to lift them out on that generator? That's awful. So no, that time is ridiculous. Now the question is, do we even have enough fuel in that generator to do it? Well, if you look up energy density of gasoline, you get 34 megajoules per liter. You can get the figure for per kilogram as well, but just search for energy density. So a single liter of gasoline would give us 34 megajoules, but only 30% of it is available, right? Because I said 30% efficiency. This means when you multiply that by 0.3, you get 10.2 megajoules of energy available. We need 2.9 megajoules to lift the elevator, right? So you got plenty of gasoline. That 1 liter is good. However, you need roughly 3 versus 10. Is the efficiency of the generator the only thing that counts? Are there any other energy losses? Well, obviously, the electric motor itself can't be perfect. So you might still only have 70% of this or so left. Really, by the time it goes through the motor, gets lost a bit of heat on the motor, friction of the cabling system in the elevator, you might be trimming it down a bit. If you're leaving that backup generator filled for a long period of time, I might not be really satisfied with 1 liter. And it's gasoline, like it's like $1 worth of gasoline. But obviously, we don't have anything like the power we need. So what would you want to change on this generator to make this evacuation of the mine safe? And that's the kind of thing that a safety engineer would be calculating. So you see sort of the difference between a pure, we're just calculating numbers we find in nature versus being given a problem and solving or analyzing it from a mathematical and physics viewpoint.